Hello students, so far we discussed relations, definitions of relations through examples, then representation of relations through examples. How to represent relation? We can represent a relation in set builder form, in roster form, then pictorial form, and also graphically we can represent a relation. Also we know how to find the domain, codomain and range of a relation through examples we discussed so far. So today we will discuss type of relations. Already we discussed previously, but today through examples we will discuss details about the type of relations. Type of relation, first is your empty relation. You know, when a relation is said to be empty, as the name suggests, a relation R on a set A is called an empty relation if no element of A is related to any element of B. That means if R from A to B is a relation, then you cannot find the ordered pair based on this relation. That means R equal to phi in this case. So there is no elements of set A which is related to any element of set B. In this case we can say means we are unable to find the ordered pairs. So the set will be, the relation set will be, which previously you know the relation is nothing but a set of all ordered pairs. So here we are unable to find the ordered pairs, therefore R equal to phi, which is a empty set. Now let us discuss this empty relation through an example. See, suppose your set A containing elements 1, 2, 3, another set B containing elements 5, 6, 7. Then if we are defining a relation R from A to B, R from A to B is a relation such that R equal to all those ordered pairs, collections of all those ordered pairs such that x plus y equal to 22. Now you see here, if you are finding all the ordered pairs of set A and set B, so what will be this? 1, 5, 1, 5. So find your sum, 1 plus 5, that is 6. If you are taking the ordered pair 1, 6, then sum is 1 plus 6, 7. If you are taking the ordered pair 1, 7, sum is 8. Similarly 2, 5, sum is 2 plus 5, 7. 2, 6, ordered pair, the sum is, as per the relation, 2 plus 6, it is 8. Similarly, if we are considering the ordered pairs 3, 5, then relation will be 3, 5 such that 3 plus 5 will be 8. Similarly, 3, 6 ordered pair, in 3, 6 ordered pair, sum is 9. 3, 7 ordered pair, sum is 3 plus 7, that is 10. So there is no ordered pairs such that the sum of the first and second element is 22. So in this case, you are based upon the set A and B, and basing upon this relation, you cannot find the ordered pairs here. So R is an empty set. So this is an example of empty relation. Then also previously we discussed about universal relation. So what is an universal relation? So second type is an universal relation. So what is a universal relation? As the name suggests, a relation R from a set A to set B is called an universal relation if each element of set A is related to every element of set B. Here we are, in case of empty relation, we are saying that there is no elements of relation A which is related to any element of set B. But here we are saying each element of set A is related to every element of set B. That means it is nothing but the entire Cartesian product A cross B. So if the relation R is the entire Cartesian product A cross B, then it will be universal relation. That means if R from A to B is a relation, then the relation is a universal relation if R is the entire Cartesian product of A and B. Let us discuss this through an example. Let us consider a set A of elements 4, 8, 12, another set B of elements 1, 2, 3. Then if we are defining the relation R equal to all those collections of all those ordered pairs such that X is greater than Y. So in this case you find out the relation. So collections of all those ordered pairs such that the first element is greater than the second element. Now if I am considering the ordered pair 4, 1, see 4, 1, 4, 2, 4, 3, then 8, 1, 8, 2, 8, 3, then 12, 1, 12, 2, 12, 3. Now this is a set of all these ordered pairs. Now see this relation, you can consider all these ordered pairs. You can consider why? Because in all cases, in each ordered pair, the first element is greater than the second element. 4, 1, first element is greater than second element. Similarly here 8, 1, 8, 2, 8, 3. All cases the first element is greater than second element. Means the entire Cartesian, all the ordered pairs from set A to set B you can consider. Means this R is nothing but the entire Cartesian product of the given two sets A and B. So this is an example of universal relation. Now after universal relation, next we discussed reflexive relation. Third type is reflexive relation. As we discussed previous classes, already these relation definitions we have discussed. So today we are discussing only the examples of this type of relations. So a relation R from set A to set B is called reflexive relation. When it will be reflexive? If R equal to collections of all the ordered pairs of this form. Set A to set A. Means a relation R from set A to set A, that means in other words a relation R on set A is a reflexive relation if the ordered pairs will be like this. Means A is related to A. Each element is related to itself. Then this type of relation is called reflexive relation. It will be more clear through examples. So let us consider an example of reflexive relation. Suppose A is a set of elements 2, 3. Then R from A to A is a reflexive relation when if if you are finding the ordered pairs from A to A cross A, so what are the ordered pairs? Ordered pairs will be means A cross A, you are finding 2 3 2 3. That means the order pairs will be 2 2 2 3, 2 2 2 3, 3 2 3 3. So these are all possible order pairs of the Cartesian product of the set A cross A. But in the relation, which order pair will consider? AA means 2 2. So R collection R will be reflexive relation if the order pairs will be 2 2 3 3. So 3 3. That means the in the individual element is related to itself, means 2 is related to 2, 3 is related to 3. So these two order pair only in this case you can consider. So if R is only these two order pairs, in which case in each order pair individual element means first element is related to second element. So this type of relation is reflexive relation. The next is, after reflexive relation, then symmetric relation. So symmetric relation means if R from A to A is a relation, then in case of symmetric relation, the relation will take this type of order pair. Means if A is related to B, then B is also related to A. What is AB? Such that this AB belongs to set A, because we are considering single set, so that means both the elements are from this set A. So means if a order pair is there AB, so means A is related to B. So if at the same time the order pair BA will be there, means B is related to A, then you can say this type of relation is symmetric. For example, the same example you can consider. Previously we have taken set A as 2 3. Now if R from A to A such that the R is, if you are considering only the, you know how to find the Cartesian product of set A and A cross A, 4 order pair you can get. But if the R is the relation of those order pairs, means if you are considering the order pair 2 3 and only 3 2, that means 2 3 3 2 you are considering, then this relation will be symmetric. Means here 2 is related to 3, this order pair is present in the relation, and simultaneously 3 is related to 2. This also, order pair also present in this relation. So this type of relation is a symmetric relation. Then after symmetric relation, let us define another relation, another type, that is transitive relation. So when the relation R is transitive, let R from A to A is a relation, means R is a relation and set A, then this relation will be transitive if it will consider this type of order pairs, means AB, BC, CA, such that this A, B, C, all the elements are present or belongs to set A or from set A. So means if a order pair is AB present in this relation and BC, another order pair is present in this relation, then AC, this AC will also be present in relation. If these 3 order pairs are present in this relation, what is ABC? ABC are from set A. Then this type of relation is called transitive relation. Transitive relation. For example, if we are considering a set A of elements, minimum 3 elements you have to consider A, B, C. Suppose we are considering elements 1, 2, 3. Then R from A to A such that which type of order pair it will take? Then R will be, if we are considering the order pair 1 2, then 2 3, then 1 3, then this relation is called a transitive relation. After transitive relation, next is equivalence relation. So what is an equivalence relation? Previously we discussed R from R on set, relation R on set A is an equivalence relation if this relation satisfies all the three types, means R is reflexive, R is reflexive, R is symmetric, next third is R is transitive. So means if a relation is reflexive, symmetric, transitive at a time, then the relation R is called an equivalence relation. Let us discuss through an example so that you will be more clear. Suppose given a set A is containing the elements 1 to 3. So when the relation R on set A is equivalence, if which type of order pair you will consider in this relation? First, reflexive means 1 1, the order pair 1 1, 2 2, order pair 2 2, 3 3, order pair 3 3. This is reflexive, satisfying reflexive relation. Individual element is related to itself. Then if you are considering the element 1 2 for transitive, then 2 1 must be present. 2 1 must be present. And if you are considering 2 3, then 3 2 must be present for transitive relation. Then next, if you are considering, next is after 2 3, if you are considering 3 1, then for transitive relation 1 3 must be present. Now based on this, whether it is satisfying transitive relation, symmetric, reflexive satisfying 1 1, 2 2, 3 3, and symmetric 1 2, 2 1, 1 2 present means 2 1 present, so symmetric, 2 3 present means 3 2 present, symmetric. Similarly 3 1 present means 1 3 present, it is symmetric satisfied. Now for transitive case, you see 1 2 present, 2 1 present, so for symmetric 1 1 must be present, here it is 1 1. If 2 3 present, 3 2 present, so 2 2 must be here, so 2 2 is present. Now 3 1 present, 1 3 present, so for transitive 3 3 must be present, so which is here. Now all this order pair, this relation, the order pair whatever you have considered here, it is satisfying all the three cases, that means reflexive case, symmetric case and transitive case. So this is an equivalence relation. Now another type you can define an inverse relation. The last type is inverse relation. So what is an inverse relation? A relation R on set A is an inverse relation if R take this form. That means if R is considering A, B, B, C like this, what is A, B, C? So that this A, B, C belongs to the given set A. Then R inverse. Inverse of the relation R is denoted by R inverse. So which order pair it will take? It will take BA, CB, like this. So means if AB present, BA must be present. If AB is there in relation R, BA will be there in R inverse. If BC present in relation R, CB will be in R inverse. Let us discuss through an example so that you will be more clear. Let us consider the set A. Same set we can consider. So suppose set A containing the elements 1, 2, 3, and if R is a relation on A such that your R is considering the order pairs 1, 2, 2, 3, 3, 1. This is your relation R, it is given. Then if you are finding R inverse, then inverse of the relation R, it is denoted by R inverse. So it will take the order pairs. If 1, 2 is present in R, so 2, 1 will be present in R inverse. Similarly for 2, 3, the order pair 3, 2 will be in R inverse, and for 3, 1 it will be 1, 3 in R inverse. So all these are different types of relations we discussed through examples. Next class we will discuss some more problems based on whatever discussed so far. Thank you.